Hi, and welcome to our first video on logarithms. We're going to go over converting between logarithmic and exponential form and back. We're going to evaluate logarithms, and we're going to talk about common logarithms and natural logarithms. So let's go ahead and get started. All right, so to talk about logarithms, the first thing we need to do is talk about exponential functions. So here we have the graph of f of x equals 2 to the x, and we're just going to analyze it a little bit and answer some questions. All right, so the first thing I want to ask myself is this exponential function a one-to-one function? And how do we check to see if something is a one-to-one function? Well, we use the horizontal line test. So what we want to check to make sure that no horizontal line will touch the graph more than once. And we can see that any horizontal line we draw will only touch the graph once. So yes, it passes the horizontal line test, and so it is one-to-one. And in fact, all exponential functions are one-to-one because remember, all exponential functions are either everywhere increasing or everywhere decreasing. So we're never going to turn back around and be able to cross that horizontal line. So does this exponential function have an inverse function? Yes. Functions that are one-to-one have inverses, so it must have an inverse function. And to investigate that inverse, let's talk about the domain and range of this function. Well, the domain of exponential functions, remember they don't have any dividing by zero, so we don't have to worry about that. And they don't have any square roots. We don't have to worry about taking the square root of a negative number. So the domain is minus infinity to infinity. And the range is equal to, well, this one, it's not shifted or anything. It's going to start at 0 and go to infinity. The smallest possible value is 0, not including it, because that is our horizontal asymptote, and the largest value being infinity. So what does that tell us about the domain and range of our inverse function? Well, remember, the domain of a function is the range of the inverse, and the range of the function is the domain of the inverse. Those guys switch. So for the inverse function, the domain would be equal to 0 to infinity, and the range would be equal to minus infinity to infinity. So we know a little bit about the inverse function now. The question is, how do we find the inverse function of 2 to the x? Well, let's continue to investigate, and what we're going to do next is we're going to think about some values of 2 to the x and think about what some values of this inverse function would be. So we're first, in this example, we're going to make a table of values for 2 to the x, and then we're going to make a table of values for its inverse. So let's just pick some x values. I'll pick -2, -1, 0, 1, and 2. And I'll compute 2 to the x. So 2 to the -2. Remember, negative exponents just mean it's on the wrong side of the fraction bar. So that's 1 over 2 squared, which is a fourth. And this is 2 to the -1, which is just 1 over 2, which is a half. 2 to the 0, which is 1. 2 to the 1, which is 2. And 2 squared, which is 4. So there are some input and output values for our function, and for our function f of x equals 2 to the x. So that means if we think about this inverse function, it would take an input of 1/4 and spit out a -2. It would take an input of 1/2 and put out a -1. It would take an input of 1 and put out a 0, 2 and put out a 1, 4 and put out a 2. So this inverse function would tell you the exponent you put on 2 to get to 1/4, or the exponent you put on 2 to get 1/2, to get on 1, to get 2, to get 4. So it's telling you the value you need on the exponent to get to a certain value of the function. So that's exactly how we define a logarithm. That is what a logarithm is built to do. It's built to be an inverse function for an exponential. So that's by definition how we came up with those. When we read a logarithmic function, it looks like this. It would look like log base 2 of x. And we read that as the logarithm base 2 of x. The base of the logarithm is the same as the base of the exponential function for which it's its inverse. And that means what power do we raise 2 to get that value of x? So if f of x is 2 to the x, then f inverse is log base 2 of x. So let's practice computing some logarithms now, remembering this. So thinking about this, let's look at the first value in our example. It says log base 2 of 16. So this is asking us, What power do we raise 2 to be equal to 16? Okay, so 2 to the what gives me 16. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So that means this is equal to 4. Because 2 to the 4 equals 16. Or let's try to the next one. What power do you raise 2 to get to 32? Well, we know 2 to the 4 is 16. We need to go one more time to get to 32. So this is equal to 5 because 2 to the 5 equals 32. And what power do you raise 2 to get to 1/2? We'll practice one earlier. This is equal to -1 because 2 to the -1 equals 1/2. All right, let's keep practicing evaluating some logs. So here is a really important formula to really help you understand logs, and I would also absolutely put this on my note card. Log base b of x equals y is the log form, and it means exactly the same thing as b to the y equals x, right? The bases are the same, right? Base is always going to be the base of the log is the base of the exponent, and I always think b to the y equals x. That kind of helps me, that little circle. So the domain of our logarithmic functions is going to be 0 to infinity. We thought about that with our inverse, but really what we need to think about is you couldn't take a base to any power and get a negative number. In fact, you couldn't take a base to any power and get 0. Like you can't take 2 to a power and get nothing. You're always going to have some fraction of 2. That's what the exponential function tells us. So the domain of any logarithmic function that hasn't been transformed or shifted is 0 to infinity. And the range is minus infinity to infinity because you can take a base to any negative power or a positive power. It's going to make a smaller number or a larger number, but you can take a base to any positive or negative exponents. And so let's investigate a little bit further. Why can't we take the log of a negative number? So let's look at this example. If we were thinking back on base 2, what would we raise 2 to? 2 to the what would get me -4. Well, 2 to negative numbers get me small fractions because like 2 to the -1 is a half. 2 to the -3 is an eighth. 2 to the -10 is 1 over 1024, I think. 1 over 1024. None of those are going to produce a negative number. It gets really, really small. It gets really, really close to 0, but you're never going to get a negative number. So there's nothing you can raise 2 to get to a negative number. So you cannot take the log of a negative number. So this does not exist. All right, so what we're going to do is we're going to practice writing our logs in exponential form to help us figure out the values of these logarithms. So I'm going to do the first two, and then I'm going to let you guys try some and whatnot. So the first one says log base 5 of 125 equals y. So rewriting this in exponential form would be 5 to the y equals 125. 5 to the y equals 125. And now we ask yourself, what do you raise 5 to get to 125? Well, 5 times 5 is 5 times 5 is 25, times 5 is 125. So y must be cubed. So that means that log base 5 of 125 equals 3. All right, let's try one more. The base of this is log base 10 of 1/10 or 0.1 equals y. So 10 to what value equals 0.1, also known as 1/10. And that answer is -1, because we can think of 1/10 as also 1/10, right? Those mean the same. So this means that log base 10 of 0.1 equals -1. Or actually, I'm going to do one more with you because I haven't talked about natural logs yet, and I just stuck it in here. So when we see this ln, this is what we call a natural log. And it uses base e. When we talked about exponentials, we talked about e before. It's a very useful base for logarithms and exponents. So natural log ln is just the same as if we wrote log and then we use that little number e of 1. Right, so that's the same thing. And now we can rewrite this in exponential form. E to the y equals 1. Well, what value do I raise e to get to 1? Remember, if you raise any number to this power, you get 1. Yep, that's 0. So the natural log of 1 is 0, because e to the 0 is 1. All right, why don't you guys try the next two problems? Pause the video, see if you can figure them out. They're getting a little bit trickier. See if you can figure the next two values out, and then we'll go over the answers together. Actually, there's 3. Try the next 3. Sorry, I wasn't zoomed out far enough. Try the next 3 and pause the video. All right, let's go ahead and go over these. So let's rewrite an exponential form, and you're going to be like, that one doesn't have a base. So I didn't tell you this, and maybe you know this from before. If not, you're finding out now. If no base is written, it means log base 10. So it's the same as saying log 10 of 1 over 100 equals y. So we write in exponential form, 10 to the y equals 1 over 100. And so first we need to get it in the denominator. So you know y has to be a negative number, and then we need to think, how many powers do you raise 10 to get to 100? And it's 2, so this must mean that this is negative 2. So log of 1/100th equals negative 2. All right, this one is a little bit tricky. So let's rewrite this. 7 to the y equals the square root of 7. Well, it might have been a little while ago, but maybe you remember that the square root is the same as raising an exponent of 1/2. So the square root of x is the same as x to the 1/2 power. So this is saying 7 to the y equals 7 to the 1/2 power, and therefore y must be equal to 1/2. So log base 7 of square root of 7 equals 1/2. And then f is pretty straightforward. 3 to the what equals 3, and sure enough, that's 1. So we say log base 3 of 3 equals 1. All right, let's keep talking about logarithms. As we saw before, we saw 2 special log functions that I kind of snuck in there for you. The common log is base 10. We used just log with no base written, and that just means base 10 because we use it a lot. And the natural log uses base e, and that's where we see that ln notation. All right, so let's go ahead and, oops, mess up my screen. Let's go ahead and practice calculating some logs in my calculator. Now, most scientific calculators have base 10 and natural log. Desmos online scientific calculator, you can actually tell it to do logs of any base, but that's probably not the one that you have in front of you. So let's just pull up a scientific calculator, and here's mine. I'm just going to pull it up, and I'm going to use it to compute some logs. So you'll see my LOG button, and I'm just going to push that. Oh, it didn't like that. Oh, here we go. I've got to put in the value first. So 100, and then I take the log of that, and it tells me log of 100 is 2, which makes sense because 10 squared is 100. 2. Oops, I have to push the pen button, 2. And what if I tried to compute log of 21? So let's clear that. And I put in 21, and I hit the log button, and it gives me a big, long, gross decimal. And that is because you can't take 10 to any power and get 21. 10 to the first power is 10. 10 to the second power is 100. 21 is in between there at about 1.3. So we can't find the log base 10 of 21 exactly. We can find this decimal approximation if we're doing a story problem or want like an answer. We can use this. But if we wanted an exact value, we would just leave it as log 21. If we want a decimal approximation, we could write 1.32. So I'm going to change this equal sign to an approximate sign. Oops. And I'm going to write 1.32. All right, let's keep going. Let's see if we can find a natural log of 277. So you type 277, you hit natural log, and again, big, long, gross decimal. That means it's approximation, and that means there's no e. You can't take e to any value and get 277, so we're just going to put 5.62. And make this approximate. And finally, let's take the natural log of negative 13. So negative 13, negative 13, and take the natural log. And my calculator says invalid input. Why would that be? Ah, I know. It's because you can't take the log of a negative number, right? There's nothing I can take e to. I can't raise e to any exponent and end up with a negative 13. So invalid input, your calculator will say something similar. And so what we just write here is, no, or does not exist. Not in the domain, any of those things. So you can never take the log of any type of log of a negative number. And those are my answers. I just went through those for you guys so you can see the answers again. And now let's talk again about exact solutions versus decimals one more time because this is just really important. Log of 3 is an exact solution. It may not feel like a solution to you at this point. It doesn't feel like an answer, but it is. It is an actual number, and you can just leave your answers that if it asks for exact solution. If you want a rounded, approximate solution, you can put something like 0.47. Likewise, natural log of 7 is an exact solution. This looks crazy. I don't know why this natural log is here. Scratch that. Log 5 over natural log of 4, also exact solution. So unless you can actually make it come out to a nice whole number, you can just leave the logs in your answers. Again, if you're doing story problems, go ahead and find those decimal approximations. All right, well, that was our introduction to logs.